Okay, so just sort of quickly before we get started, there are a couple of links on that sort of like lectern information thing at the front. Those include a quick glossary that's sort of like if you ever have certain definitions or questions as you like hear them come up during the lecture and like you miss when we're explaining or whatever the case might be, there's a good little resource there by Google. And it explains a lot of these concepts rather simply, and I think it's just a good reference to have. There's also and Alan has been kind enough to post it in chat as well. That's awesome. There's also a Colab notebook, which will actually be our coding component. I'll go over the steps involving that in a little bit. So we'll do that after a little presentation. And then we also have one other quick feedback form.
All right, so it's 5 past, so let's get started. So welcome to our Devs AI and Machine Learning workshop. I'm Akash. I'll be going through the first part of this workshop.
Yeah, and I'm Krithik, and I'll be, intermittently talking about things and going over the coding part of this workshop.
Cool. So here is the game plan for this workshop. We're going to start with an overview on machine learning and talking about what machine learning is and the different types of learnings. And then we're going to go into a high-level overview into reinforcement learning and recommendation algorithms. And then we're going to move on to the core of our workshop on computer vision. And the majority of this workshop will be us actually building our own neural net. Cool.
Very cool.
So before we get started, we just want to give a big shout out to our sponsors. So our gold sponsors is Potentia, SensNet, Atlassian, Serato, Nintex, Optiver, Zero, Canva, and Gather. So quick housekeeping thing. If you guys haven't used GatherTown before, we have a thing called Spotlight Tiles, which is basically the stage where we're standing at. And there's a little Spotlight tile where you can ask questions just on the top right side. And basically, the moment you step on one of these, your audio and video will start broadcasting to everyone. So just make sure when you guys are running around, you don't want to accidentally step on one of those. We also have private spaces. This is where you can hear all the broadcasts that me and Krithik will be talking about, but the audio from you guys won't be heard to other people. So yeah. Cool. So let's get started with the content. So what is machine learning? Machine learning is a field in computer science that tries to learn patterns from data and make predictions based on that. And the algorithms that actually make predictions and learn the patterns fall into the following 3 categories: supervised, unsupervised, and reinforcement learning. So supervised learning is known as the learning through examples. So let's say, for example, we wanted to predict whether a certain image has a bus in it or not. We would pass in a bunch of images that are labeled. So we'd say whether or not they have buses in them. And then using this as an input, we can then build a model with the input images, and we can use this to predict the values of the unlabeled data. And we'll go through in our computer vision topic on how we actually learn these patterns. Cool.
Great. So unsupervised learning is a little bit different. It doesn't have like a discrete set of truths attached to it. So models like Siri, Google, Google Assistant, Alexa, and quite a few others, like even CycleGAN, for example, which is like a very complicated machine learning model for generating images. They don't have something like something we would call ground truth. So they have to make implicit associations about characteristics inside of that data. So for models like Alexa and Siri and like visual and text processing models, the attempt is to make relations between specific words. So like, for example, if like king is to queen, as man is to woman, or whatever the relations may be. And attempting to understand that is done through large volumes of data. Unsupervised learning lends itself to very, very big models. So GPT-3 includes roughly a billion trainable parameters, which is quite a big feat, and it takes a lot of computational resource.
Cool. So reinforcement learning. So I explained that supervised learning is the learning through examples. Reinforcement learning is the learning through experience and trial and error. So here we can see a cool GIF on simulation of hill climb racing, and you can see many generations trying to slowly learn how to master the game.
Yeah, fun fact. On the right-hand side, that's AWS Deep Racer. If you guys are interested, that's a contest you can compete in. It's a reinforcement learning contest where you can buy the kit and then compete in like AWS races, and you get free AWS credits for it too.
Yep. And we have a quick video, which I'll share.
Here's the problem. The elephants need to be able to pull the table closer to gain access to the sunflower.
Okay. Oh.
Uh-oh.
So while this ad is sort of playing, so the objective, like they explained it, they're like two drawstrings, and like these children had to work together, and obviously these are young children, but they still figured out that they have to work like with each other to get the reward, right? So we've tried this test on multiple different animals. Like apart from like primates, very few animals have been able to successfully do this task. So we're about to watch elephants attempt to do it, and it's very
quickly share the presentation again. Oh.
In case you want to watch like just that video, I posted it in.
All right, so you're probably wondering what was the point of that seemingly unrelated video on reinforcement learning, but the point was that the elephants were put into an environment and they were trying to solve a multi-step goal within that through trial and error. And this is essentially what reinforcement learning is all about, and it tries to emulate this process. So the basic learning framework for reinforcement learning is that you have an agent or agents that are put into an environment, and the agent then senses its environment and executes an action. This action would cause a change in the environment, and then the agent observes this new state, and receives a reward based on that. And the reward element of this is basically just a positive signal or a negative signal, which basically tells the agent, good job, and do that again, or bad job, and don't do that, try something else. So here we see a GIF of cats learning to press a little bell, and that when they do that, they get a little snack. Cool. So we've seen that theory base, but let's check this video.
For those of you who don't know, this is developed by a company called OpenAI. So it was initially funded by Elon Musk, but it's one of the most like prestigious artificial intelligence and machine learning like places to work. So a lot of research on ethical research is being done at OpenAI. Meg, sad.
The evolution of increasingly intelligent life forms. Today, we ask if
so sort of provide
multi-agent competition can also lead to intelligent behavior in a new virtual world.
So they explain this a little bit, but essentially these models, the red ones are seekers, find hiders, and then the blue ones are actually hiders. They're given no prior information about their environment.
After training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools.
So the reason why this is interesting is that, like, given no information, all of these individual agents are trying to optimize their own situations to rewards.
Even so,
But the cool
the
thing
hiders
is
learn
that similar to what the elephants had to go through, they realized that like if they don't cooperatively work with each other, that they're gonna face roadblocks in stopping the seekers. Um, and then similar to like trying them with different testing environments, they also used reinforcement learning models and gave them different tools, environments, without really telling them what they do. And it gave a very surprisingly powerful set of results. You'll see the simulation get progressively more complicated, but the idea is very clever. So now you'll notice that they start like literally taking the ramp away from the seekers. So like, okay, if the ramps are providing them with the ability to get us,
more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures.
it's very cool because now you're starting to see them
Seekers
slide
from
as well.
using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learned. However, we found that after more training, the Seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observed, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide-and-seek in parallel for many days. They train against each other, as well as past versions of themselves, using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior
Okay,
from
so
multi-agent
sort of
interaction.
the last like remarks here.
We hope that with a much
There are
larger and more diverse environment,
simulation that were run, and the cool thing is that there are some variants of this thing that like the hiders ended up boxing in the seekers because they're the only ones that are able to tangibly change the placements in the environments. So machine learning, obviously, because it attempts to find patterns in data, if it's able to optimize for a specific like meta, if you will, it will absolutely like take advantage of that. And you'll notice that like when people started doing this for old emulated games for like Nintendo 64s and whatever, a lot of these games had bugs in them that these models implicitly found just from like millions of generations of trying that started exploiting games. And it's very interesting to watch. There are plenty of documentaries on it.
Yeah. So before the machines can truly take over, there are some challenges with reinforcement learning. And that's that most of the experience that the agents receive are through simulation, as we saw in that video. And so the challenge becomes actually transferring that knowledge from the simulation into real life. So the two main solutions that are being researched currently are either to improve the reinforcement learning algorithms so that they're transferable to the real world, or actually improve the simulations themselves to be more realistic. But both of those features are easier said than done.
A notable example of this is Waymo and so Google's self-driving car division and like Tesla. So they use reinforcement and simulation learning models to train their things. So the attempt is to do something called like the billion-mile simulation. So it's 1 billion miles of fully simulated environments that the cars are meant to go through, but it's they find difficulty in transferring these into physical cars. So they have to constantly iterate through the data. It's a very cool branch of machine learning.
Cool. So let's move on to recommendation algorithms. This is one that it's one of the most prevalent uses of machine learning, and it's used in YouTube, Netflix, TikTok, Amazon. All the major corporations use it to recommend products. So a quick thing about the motivation and the importance of recommendation systems is that corporations are essentially fighting to grab our attention, and so that we can use their products, so then we can either view more ads like on YouTube or make more purchases on Amazon. And both of these would result in more money for the corporations. So one of the best ways to grab and retain our attention is using recommendation algorithms. So yeah, go ahead.
Oh no, sorry. I was just.
Yeah. So one way that recommendation algorithms are used is through collaborative filtering. So basically what this is they look at similar users to yourself and make recommendations based on them. So a quick example on how this works is, let's look at the example that we have here. So let's say we have a platform that has 6 pieces of content, and we have 3 users on that platform. So we want to predict what user 1 would rate content piece number 5. And these blank spaces are either because they haven't viewed the content or they haven't given a rating. So we're trying to predict what user 1 would think content piece number 5 is based on what user 2 and user 3 think. So what we do is we first compare user 1 to user 2 and 3 to find out how similar they are. So here we look at the similar rows to each other. So basically for user 1 and user 2, we look at columns 1, 2, and 3, 1, 2, 3, and 4, because they share those observations. And with user 1 and 3, we look at columns 1, 2, 3, and 6. And so we can see the 2 vectors here. So now what we try to do is we try to create a metric for the similarity. So one way to do this is using cosine similarity. So basically how this works is we use the function here where we take the dot product of these 2 vectors and we divide that by the magnitude of the 2 vectors. So if you guys remember with your math, like the smaller the angle with a cosine, the closer the value is to 1. So in this case, the more similar the 2 users are, the closer the similarity value is to 1. So as we can see in these 2 vectors here with user 1 and 2, we can see they're like very similar. Only one observation was different. And so when we calculated the cosine similarity value, we got 0.99. And so, yeah, say it.
Oh, no. I was just like, does anyone want to try to make a guess of what kind of machine learning like subclassification is this? Is this supervised or unsupervised learning? Feel free to drop that in chat. Good guess, Tyler, but it's actually unsupervised. So it's a little tricky, right? So you would think that there's a truth label. No. I it's very understandable. So you would think that there's a truth label, but a lot of these, right on, Bose. So the reason why this is unsupervised is because there is no actual label to the recommendations. It's attempting to look at the similarity and make assessments. So it's a predetermined formulaic thing. So you can see the cosine similarity algorithm there. Just fun little side fact.
Yeah. So using these 2 similarity values, we can actually use them as weights to calculate the estimated rating for content 5 for user 1. So if we take a look back, user 2 rated content number 5 of 5, and user 3 rated it at number 3. So we can just use these weights and then divide it by the sum of the 2 similarity values to get the estimated rating, which was 4.15. So then if we look at this on a high level on instead of looking at it from 6 pieces of content and 3 users, with it being a large number of content and a large number of users, basically what we can do here is we can estimate the values for each of the blank spaces here that users haven't seen, and then we can rank that accordingly. So we can grab the highest values for the estimated rating, and then that's how we send the recommendations across. Cool. So I'll pass it over to Krithik now.
Awesome. So this is going to be the primary of what our workshop and actually coding up is going to be about. So we'll be coding up a convolutional neural network to do some image classification. So computer vision is one of the most well-established branches of like machine learning in general at the moment. So we use computer vision from everything from like diagnostics for like medical things. So we've gotten to the point where like we can detect melanoma better than a good number of dermatologists can, and that it's becoming used in clinical use now, which is really interesting. Apart from that, we also use it for stuff like Tesla self-driving to identify different objects inside of a frame, and also like object classifications. So it's a very robust field. Next slide. So just to give a little bit of perspective as to the rationale behind how we want to approach these problems. So in computer vision in general, or like in machine learning in general, and more specifically in computer vision, we want to try to understand how we as humans perceive things, understand things, and procedurally attempt to learn, if you will. So for machine learning models, from like a purely neuroscience perspective, this is a very like simplified version, mind you, but essentially on the right-hand side at the very top, the blue thing is a simplified version of a neuron in our, like a neuronal cell in our body. So these are the compositions of what makes up our brain. And then right underneath it, we have what is a very simplified, but still a actual computational and mathematical representation of that. We call these neural networks. So in a traditional machine learning model, we have about a couple billion, like anywhere from a couple million to a couple billion of these. In the model that we'll be building, it has like somewhere in the neighborhood of 3 million of these neural networks or trainable parameters and like actual individual neurons. The interesting thing is that, does anyone want to take a guess at how many our brain has roughly? If you're within a magnitude of 10, I'll take it. I'd be surprised if anyone. 2 cells. That's not bad. 3 billion, 100 billion. Okay, so all like actually decent guesses. It's actually in the order of 1 trillion. So the largest models that we've developed as humans that we've been able to successfully train and use was also developed by OpenAI. It's called GPT-3, and it's like a text processing thing, and it has like somewhere in the neighborhood of like 2.1 billion parameters. So we on a objective scale are about 1,000 times more powerful than a machine learning model at like generalizable thinking, which is very interesting to think about. So that's sort of like how I wanted to preface this, and then now we can get into some of the more technical and complicated stuff. So next slide. So the way that we want to think about this, and this GIF plays, okay, cool. So the way that we want to think about convolutional neural networks is sort of the way that we like try to read a book. It would, Meg, that's a great question. It would take a lot of computational power and would also read some other more sophisticated problems that I can talk about in a little bit. But to sort of explain CNNs first, the idea is sort of like how you'd read a book. So if you were to just stare at a page without reading any of the content, obviously you don't derive any of the information from it, right? So we have to read it in whatever direction that we choose to go and scan over to sort of compile information about what was on that page. So the way that convolutional neural networks work is actually very similar. They scan over an image to gain like the most important features that it has defined as useful towards a classification. It then compiles these features in a convolved feature. We'll get more into like some of the semantics behind this, but it's very interesting. In the workshop, we'll actually go over the process of trying to visualize some of these, because while it may be very easy for us to visualize differences between, say, an apple or an orange, the features that a convolutional neural network or machine learning in general picks up on are very different. Okay, next slide. Cool. So now, this is the, not to be intimidated, this is actually not that bad. Fun fact, you don't even have to code the algorithm in front of you. We're just going to quickly go over the idea of loss functions and how classifications actually occur. Okay, so if I were to sort of pose this as a question of like, okay, you looked at an image, you saw a couple of features, and you're like, okay, this is definitely an orange. But then I tell you that it's not. And you're like, dang, I thought I really knew the difference between an apple and an orange. So essentially, machine learning models go through this process constantly. And what ends up happening is that there's this very complicated, like multi-dimensional space that exists, and it's called, or like rather the optimization of this space is called gradient descent. So what you're trying to do is that in this very complicated space, you're trying to find the minimum point that exists. So on this like right-hand side, you'll see this like little trajectory, and it looks like you're like hiking down a mountain, right? And that's essentially what machine learning models are doing, is that they're looking at all of these parameters inside of this model, inside of your data set, and then trying to distill it to find optimality and generalize about the learning features. So that's on the loss function. And then next slide. Don't worry if this is all a little much. We will be going through this a little bit more in depth in the coding part, so not to worry. But essentially what we'll be doing today is going through the process of actually building a machine learning classifier that classifies between cats and dogs. I know this is a very difficult task. Obviously, as humans, we're not able to do this. So clearly we need a computer to do this for us. But all jokes aside, essentially the idea here and what you're seeing in this animation is that this is the process of gradient descent and backpropagation. So there was an initial evaluation that this model's prediction was, oh, it's a cat, but it was actually a dog. So it goes back through all of those neurons that we just talked about and corrects which ones were incorrect. So it'll be like, oh yeah, this activation here that thought that this feature was related to a dog is actually related to a cat, and then goes back and corrects them. So next slide. And I think that's, okay, cool. So this is what we'll actually be building. It looks very complicated, but trust me, it does not take a lot of code. And you'll be very gratified after you finish building this. So essentially what we have here is the entire architecture of the convolutional neural network that you'll be building. So you take in the original image and then you perform some of those convolutions that we talked about. So every single one of these 5x5 instances is actually called a filter. So it tries to extract different kinds of features from the network based on some sort of criteria. The criteria to us is a little bit unknown, and we spend a lot of time attempting to understand this behavior. We can somewhat generalize mathematically, but for large volumes of data, it's hard to like nitpick exactly what it's looking at. So we repeat this process for a couple of times just to better understand exactly what's going on with the model. And then we do something called like the fully connected layer, where we flatten all of these inputs and then try to make an assessment with one classification of what exactly is going on. Cool. Oh yeah, we will play this with caution. This is
One sec.
we are as YouTube would say, we are family-friendly content. But Silicon Valley is one of my favorite shows of all time, and it's just really funny. And this is a little bit of insight into pretty much exactly what you'll be building, but you know, hopefully tries to motivate you a little bit more. Very close. It's hot dog, not hot dog. Yes. Takahiro, you're pretty much on the money there. Although not sausage is also not hot dog. So I think
that is a burrito for the test. Good to know.
Oh, let him have it. Guildford thought he was too good to work on seafood, and now he's about to lose a fortune.
Okay.
Ready
this
for
is
test?
like one of my
Are you
favorite
ready?
episodes.
Oh,
So
this
good.
is weird. Mia just texted me, good luck with the demo. Did any of you guys tell her about this?
Your hacker girlfriend wouldn't happen to know the model of our router, would she?
Yeah, actually, she complimented your choice.
Why didn't you say anything?
Why would I tell you she said something nice about you?
Damn it. You have to assume she's everywhere.
Okay.
Okay.
So this is all the build
Ready.
up, but like you're gonna get ready for the next like greatest innovation.
What will you say
You guys
if
are
I
building
told
this.
you there is an app on the market?
We're past that part. Just demo it.
Okay. Let's start with a hot dog.
Look, guys. It classified the hot dog. Isn't that crazy?
Ah, motherfucker.
Huzzah!
Jin Yang,
It's-
my beautiful little Asiatic friend. I'm going to buy you the palapa of your life. We will have 12 posts, braided palm leaves. You'll never feel exposed
You
again.
you
gonna be
too
rich.
can have a palapa
Fuck you,
after you build this
Guildford.
model.
Do pizza.
Let's do pizza.
Yeah.
Okay.
Palapa not included.
Pizza.
Not hot dog.
dog.
And
Wait,
that's
what
what
the
we'll be building today, but for
That's-
cats and
that's it?
dogs.
It only does hot dogs.
No, and a not hot dog.
Give me that. Give it to me.
Okay. So who's ready to build their binary machine learning classifier? Very exciting stuff. So getting started here, we're gonna start off by copying your this workshop right here. Can you drop it in the chat again, like the collab? The one that's empty? For some reason, I have the one that's not empty. Oh, nope, never mind, found it. I have the non-empty one too. Cool. So just to get quickly started, I'm gonna go through a quick presentation, but this is just to follow along. So we're gonna drop the chat, a collab. You don't have the ability to edit this, but don't attempt to edit this. You're gonna make a copy of this, and we're gonna be using this for our little coding workshop here. So share. It should also be at that lectern in front, but in case that you don't have it, it's in the chat now. So getting started here, I'm going to share my screen just to sort of go over exactly what we're going to be doing. Okay, slideshow. So getting started here, what I want you guys to do is create a copy of this in your drive. So we're going to get a couple of these things set up. So what you're going to do is click on File once you open that collab, and then you're going to say Save a copy in Drive. And then you're going to want to open that copied version. So this is the one that's going to allow you to edit all of this information and actually complete the coding workshop. So far, so good? Has everyone been able to generally get a copy of their collab? Give me a quick thumbs up or like a yes in chat, and like I'll be able to. Perfect. Okay. Oh, perfect. Okay. Seeing a good number of thumbs up. That's great. Awesome. So the next step that I want you to do is double check that your runtime. You're going to click change runtime type in case. And then if it doesn't say that your hardware accelerator is a GPU, I want you to click on the dropdown and then change it to a GPU. Same thing, a yay or like a thumbs up. Once you have that all set up, that would be great. Cool. Getting some good responses here. Okay, Tyler. Yeah, great question. So essentially what you're going to want to do, yeah, absolutely, not a problem. So what you're going to want to do is when you click on runtime, so on your copied Colab notebook, you want to click on runtime. You're going to go all the way down to change runtime type. So here, under hardware accelerator, you want to make sure that GPU has been checked off. So if you don't have your GPU activated when you open up your Colab, you're going to hit a bit of a problem with your machine, like your neural network taking a very, very long time to train. Cool. How's that going for everyone else? Great, great. Awesome. Cool. If you're still having some troubles, feel free to message Akash and he should be able to sort of walk you through it, get you set up, whatever the case may be. So, getting started. The first thing that we're going to want to do, is sort of actually download our database and go through the steps here a little bit. So the first thing is just literally running this wget no check certificate. Don't worry about that. That's just like making sure that you're able to download this. We're taking a minified version of the cats and dogs data set. It's a very large data set on Kaggle if you're interested. It has like 20,000 images, but I don't think we quite have the computational resource, rather the time to do something like this. So we're going to do that, and then we're going to unzip the folder. So all you have to do is run these two cells, and you can do that by pressing the play button, or you can press Shift Enter. So far, so good? Great. Very cool. So once you've uninstalled, once you've unzipped, just for sanity checks, make sure that you have a folder by clicking on this like folder icon on this left-hand side and seeing if you have a cats and dogs filtered as a folder here, right above sample data. Again, quick thumbs up if you do. Great. Awesome. Perfect. So the next thing that we're going to do is import OS, and this allows us to sort of access file directories and get comfortable with this. So the reason why I'm spending so much time going over data input is that one, it'll be useful for the contest if you choose to compete, but also in general, the hardest part about machine learning, more often than not, actually ends up just being literally learning how to like import data and like appreciably use it as a data loader. So we're going to start off by defining one thing, and that's going to be our base directory. So looking at our file, we know that the folder that has all of our information inside of it, which is the cats and dogs filtered, is literally called cats and dogs, filtered. Cool. So we're setting this up as a string, and this is going to be useful later. So cats and dogs filtered. And then the next thing that we're going to do is start setting up the train and validation directories. So inside of this folder, we can sort of see that we have a train, which is what we're going to be using to, as the name implies, train the model, and then validation, which is data that the model won't be trained on, but to sort of check the validity of the training. So this exists because machine learning models are so good at finding patterns in data, sometimes they find patterns that exist in that very small subset of information and not the concept as a whole. And as such, we attempt to sort of mitigate this and understand this behavior by creating a validation data set. And now we're going to create the train directory. And what we're going to say is os.path.join. And then inside of here, we're going to say that base directory that we previously instantiated, and then the folder train. And then one last thing before I come back and check in with everyone, we're going to do a validation directory, which is same thing. We're going to do os.path.join, and then we're going to say base directory is equal to validation. I'm going to stop here, make sure that everyone is doing okay, and then we'll get back into it. Cool. So how is everyone doing so far? Everyone got the os.path.join? Everything is working pretty well so far? Yeah, absolutely. So this is what it's going to look like here. You're essentially just naming it. You're providing the names and the paths for where all of these folders and things exist. Cool. And I'll also I'll end up dropping the completed notebook a little bit after. I still sort of want to go through the process of actually coding it up. So if you ever need me to stop or something, message Akash or try to message me, and I'll try to get to the bottom of it. Cool. So now we're going to get into directory with training cat pictures. So as the name implies, we're going to go train cat, and then directory is equal to, and then again, os.path.join. So we're associating it with this folder, and we're going to go train underscore directory, and then cat. It's very simple. So if we were to do this for training dog pictures, considering that the dogs folder is called dogs, how would we go about doing this? If anyone wants to drop the solution in chat, that'd be pretty cool. But for dogs, sorry. Tyler pretty much got it. Tyler knows what's up, but what if it was for dogs? Exactly. Right on. So, oops. Yep, fair game, Tyler. Fair game. So let's finish this off, shall we? So we're gonna call it train dogter, and then change this to dogs, and then now we have to do the validation. So as you might have guessed, we're gonna change this to validation, and then here we're gonna change this to validation. And then cat and cats. Cool. So if you run this, it shouldn't give you any errors, hopefully. Let's take a look. If you get any errors, let me or Akash know, and we'll try to resolve it as quickly as we can. Cool. Got a thumbs up from Meg. That's hype. Everyone else doing well? This will arguably be the hardest part of this tutorial, I promise. Which is pretty rewarding if you think about it. Cool. So now we just want to do a little bit of a sanity check here. Did we actually get the correct like directories? Are we accessing the stuff correctly? So for the sanity check, what we're going to do is os.list directory. And then here we're going to do train cat directory. And then we just want to print some of the cat names. So what we're going to do is just print, you know, the first 10 or so. And then the same thing, just to try it, we're going to do the dog directory. So dog. And then we want to try sorting it just to see if manipulation of this file is actually possible. So fnames is equal or dot sort, right? And then we're going to print train dog fnames. And then same thing. So if we do this, we should see a random set here just based off the way that the directory was pulled. And then if we sort the names, we get dog 0, 1, 10, 110, 100, 101, and 102. Obviously, because it's processing them as literal strings. Does this work for everyone? Is everyone comfortable with this code? The term of art here is os.listdir or list directory in case that you need it. And then you can provide, honestly, yeah, you can provide any like validation cat directory or trained cat directory, whatever the case may be, and then just sort of validate that you're in the correct place. Everything look good for everyone? Sorry, I'm back on the screen now so I can actually legitimately see. Great, great, cool. Random question, what does adding OS do? So OS is a library. This is a good question. So OS is a library inside of, it's a very native low-level library inside of Python. And OS is the like the file management and like systems directory library in Python. It's very powerful. And if you're able to learn OS and like fully learn OS and glob, which are two different libraries for like file management, you're in a very good place. It's a very powerful set of libraries. So, or I guess, I don't know if you were asking programmatically, OS is what the, you have to specify a library and then the function that you'll be using inside of it. Oh, easily. Come on, you learned about OS? One of the most fundamental Python things? Okay, so if we're all feeling pretty comfortable here, I think we can move on to the next thing. So to get a better understanding of exactly how much data we have, we want to quickly test exactly what the length of all of these, we want to know how many training iterations that we have for any given thing. And this is rather simple. You don't have to do this if you don't want to, but in the case that you're, again, as a training exercise to better get used to something that we call exploratory data analysis in computer science, we are going to do something called len, and then os.listdir, and then here we're going to do train cat directory. And then you want to just try this again for other ones. So we're going to go dog images, and then dogdir. And then if you can believe it, we're also going to do validation. This is entirely optional. You don't have to do this, but in the case that you were curious as to how to actually, again, fully understand the contents of what exists inside of your data set, this is a good way of doing so. So if I run this, cool. Gave me exactly what I was expecting. You guys should have 1,000, 1,500, 500. Give me a quick thumbs up if that works for you. If you didn't do it, it's fine. How are we feeling? How are we doing emotionally so far? Hopefully, unlike a regular comp sci degree, this is a little less draining, emotionally draining. Okay, looking good. Very cool. So now we're going to get into some of the actual components. So here we're going to quickly visualize some of the images, just to, again, another way of just taking a look at the data. Oh, forgot to do this. We have one thing, it's cat directory and dog directory. I seem to have messed that up here, but that is okay. Quick check, and then you should see a list of 8 random cat and dogs images. So is that working for everyone? And again, if there's a problem, if there's a yellow line underneath it, just remember that means that there's probably a typo in the function name. So I had to change mine from cats to cat. So if you're able to visualize this is pre-built code, so you don't have to worry about it. You can just literally run it once you make that quick change. Cool. How's that working for people? If you don't see images, that might be a bit of a problem. Okay, we got 1 thumbs up. That's great. Perfect. Cool. You're like, can this guy get to the machine learning part? Yes. Yes, he can, eventually. So now we're going to get into the actual part of developing this model now. So to give a quick primer, TensorFlow is Google's machine learning backend. They've built this whole thing. It is one of the coolest things that has ever come to the world, probably. It has made machine learning so accessible for so many people. And we're going to be using one of the subsidiary libraries that Google actually owns, which is Keras. And Keras is a very simple and it's a very flexible machine learning thing. It's literally been used at places like CERN and NASA, which is kind of crazy. Here you can see the TensorFlow and Keras ecosystem that exists. Yeah, it is such a cool thing, and it's used for all sorts of applications. So we're going to get a little bit of a sample into what we're going to be building here. So getting started, we're going to import something called from TensorFlow.Keras import layers, and then from TensorFlow.Keras import model. Layers is literally the process of, and if we go to this presentation, building out these layers. So every single layer has a different kind of convolution or mathematical operation that occurs with it, and we'll be literally building these out by hand. And it's very cool, and it's a lot of fun. So we're going to run this quickly, and then seems I may have already given you the model. Oops. Haha. I guess you can. Maybe? Yes. Okay. Oops. I gave everyone the model already for some reason. Is someone editing this version of the document by chance? That's so weird. Okay. Crazy. Yes. I will absolutely be going through all of it. That's yes. If you'd like to go through it and type it up in Spirit and literally go x is equal to layers dot layers dot conv2v, I think it's still generally beneficial to do that. So if you would like to, please go ahead. But essentially, what we're going to start off with is attempting to understand the input layer, and this is usually the one that's the hardest. So we want to resize all of these images of different sizes into 150 by 150. So the way that we do this is that we create a layer that holds something called a tensor. So it's an array, but it's an array where some of the features don't have a concrete definition of size. It's a little weird, but essentially what we're going to do is take something called layers.input, and then we define the shape of our image. So shape is equal to 150, 150, 3. And what this is that obviously from a height and width standpoint, we have 150, but then every single image has RGB channels. So because they're comprised of 3 different color sources, and then their contributions make up an image, we separate them on a tensor level as 3 different layers. So that's what the image input layer is. Okay. So like the array describing all the pixels. Yes. So it would be 3 2-dimensional arrays that all describe the feature channels. So you'll get to visualize this very soon, but yeah, that's your intuition is exactly right. So now we begin the process of actually attempting to extract meaningful information from these images. So the way that we do that in Keras, so syntactically, is that you keep the same layer name for every single layer. So you go x is equal to, and then now we're using that layers function, and we go conv2d, which is a like the 2-dimensional convolution, and then we separate by the number of filters. So if you go back to this diagram, right? So this is a filter. So we have 1, 2, 3, 4, 5. They have 5 filters here. You're at your own discretion to use any multiple of 2, factor of 2. So it can be anything of 2 to the n. If you'd like, you can try 64. Although I generally, because the data set is so small with only a couple hundred or a couple thousand images, I would not recommend that. And then here we specify what the size of the filter is. So what is this exactly, right? So this is quite literally the size of the square. So what is, like, it is, in this case, it went from a 28 by 28 by 1 to a 5 by 5. So we're extracting this, and in our case, we're going to be using a 3 by 3 filter. So if we actually want to think about it, the most accurate representation of this would actually just be this. It's just how this thing scrolls over. We are reproducing this behavior, except the convolved feature is not going to be a 3 by 3 matrix, but rather a 2 by 2 matrix. So here we go con3d, and then we do activation is equal to relu. So another term of art here that you're going to come across is different activation functions. So what do those look like? What are they? Why do they matter? So these are activation functions. So if you want to think about it, remember when we talked about the brain being like a synapse? So essentially, we need to create similar synapses for every single feature inside of our network. And the way that we do that is by using these activation functions. They're all different kinds of mathematical formulations, but essentially the idea is that they grow somewhat exponentially from the initial activation state. So this is what's going to be a determination of whether or not a neuron fires inside of our network. And the one that we're going to be using is ReLU. So it's this one right here. So if I were to draw on this, we're going to be using this one. Actually, for all of our convolutional networks, and then we're going to be using this one for a final prediction. And we'll go over why that's the case in a little bit. But when we write the activation function, what's happening is we're literally going through this feature. We're being like, oh, this information was pertinent. This will contribute to the overall activation. It gives a little activation to the synapse. And then here we go, x is equal to layers dot max pooling, and that's the process of like extracting the convolved features, that little like mini window that we saw. And then here we specify that it's 2. And then here we specify that it's image input. And then we always give it the previous information of the layer. And then that is your first layer of your neural network, like the first actual convolution. Cool. So how's everyone doing so far? Everyone conceptually understand what's going on there? Any questions? Any sort of queries? I think people are doing pretty well. Great. So if that's the key, oh, oops. So if there's any other questions, feel free to ask. But essentially, we're going to repeat this process over and over again. And we're going to do this for a couple of different layers. So now we're going to get that window's going to get a little bit smaller. But then we're going to increase the number of filters that we're extracting from this information. So what's actually going to happen, right? So we're going to literally copy what we previously did, which is like fair game. And then we're going to increase the number of filters and then give it x as the previous value, and then max pool again with the same window. Okay, we have a question. What do you mean by filters? Really good question. So you're gonna see me visualize this a little bit in like a second here. So filters are different kinds of visual features that the model has extracted. So in our case, here's actually what a filter visualize. Your code will actually do this, and you'll get to see. But when we extract 16 different filters, this is what different, like it's taking the same input image and trying to find different like image values, histogram distributions, compositions of elements, spatial organizations, and attempt to extract that information. We don't know exactly what those features are, so we provide a variety of different filters for it to figure out which features does the model interpret as best for classification. Does this sort of answer your question, or how are you feeling about that? Cool. So it's almost like, yes, exactly. Meg, so there's actually a really cool thing, which is a little bit difficult to implement, but if you're able to do it, it's really fun to take a look at. It's called GradCam. So remember when we talked about gradient descent in that previous thing about trying to optimize the gradient inside of this thing? So understand this very complicated feature space, try to see what features are sort of lending themselves to this understanding. Well, there's this actual model, like a specific tool that we use to better understand these models called GradCam, where it's specifically when it does an activation, you look at areas of interest. Where is the model actually looking? So it's pretty stark here, actually. So if you have an image with both a cat and a dog, and you say, look for a cat, you can see that the vision is very, very strictly focused on the cat. And then the same thing is true for the dog. When you say dog, it's very strictly focused on the dog. It's a very cool phenomenon, and we do a lot of stuff on like explainability of these models by doing this. We try to like sort of emulate that process by doing it with these convolutional filters here. Yeah, but it's a feature extraction methodology. Oh. Yes, seeing how computers see, like this is why the computer thing, when I talked about like how the brain works and like how we as humans perceive and process information, is like so interesting because they're able to replicate that behavior. Okay, so finishing off this model, we're going to have a second convolution, and obviously it's been coded up for you, but if you'd like, you can try to make modifications to it if you'd want. Again, remembering to keep within the confines of the parameters that were like previously mentioned. So we create the same layer, we add another convolution process to it, but we increase the number of filters this time because now we're working with smaller subsets of information, right? So we're pooling information from the pooled information. And as a byproduct of this, we want to expand to a higher number of filters so that we can start to see if there's even more minute details that we haven't picked up on already. And then finally, we're going to do it one more time or two more times if you'd like, depending on how fancy and or adventurous you're feeling. And then it's the same process syntactically. Go X layers.conv 2D, 64 filters now. We're progressively increasing them. You can also choose to decrease them if you'd like, although some of the math gets a little complicated, and then your feature models will get more trainable parameters for a very particular reason. You can also try different activation functions. In fact, I think you can pretty much type in any of the ones that are one words here. If you'd like to try 10H, if you'd like to try sigmoid, if you'd like to try leaky ReLU or softmax, any of these are fair game. They won't lead to optimal results, but if you'd like to try them just for the sake of exploration, please feel free to do so. Oh, okay, and then that ran. So now we're gonna get into the last part of actually building our model, and it's relatively simple. And what we're actually gonna go through is the process of flattening. So because these machine learning models are kind of weird, they take these pooled features and then we take these like complicated two-dimensional arrays and then we just literally just flatten them out. We like squish them. So what ends up happening is that for all of these images, we compile them into a specific category of sequences of pixels and hidden inputs and variables. Why do we do this, right? So when we talked about a neural network, we saw all of those like weird diagrams, right? We saw like this kind of thing. Where are all of these nodes? Well, we take all of those learned features from our model, and then we provide them as this flattened array of information. Oh, let me escape out of drawing so I can actually play this. So if you look at this, what's actually happening is that we flatten the information from this array. I'm pretty sure this is a 3 blue, 1 brown video. It's really cool to watch. and they've done an excellent job explaining this. But essentially, you take this image, you smush it, you create something called these hidden features, and then you try to extrapolate the information from them. And it's a very cool process. So that's exactly what we're going to be doing for this last part. Is we're going to say x is equal to layers.flatten of the one-dimensional tensor. And that gives you that batch of images as a flat ID of features. And then we actually create that neural network here. So they use 784 hidden features. We'll be using 512. We'll use the same activation function of ReLU, but here, instead of layers.conv2d, it's going to be a dense function. And the reason why it's called dense is that obviously this is a Keras implementation, but dense means that every single node is connected to every other node. So every single node here is connected to every other node in this network. And it's a little bit easier to visualize here, but you can see that all of the input nodes here have one output to one of the hidden inputs, which is very cool. Okay, so the last two lines of our function before we actually compile the model is we have x is called layers.dropout. And the reason why we drop out, not out of university, but out of like layers in our network, is that sometimes these models learn features that aren't representative of the actual class, but rather just those specific images. So to learn patterns in those images, it was like, oh yeah, if there's like a pixel on like, sorry, excuse me, if there's a pixel on like the 27th row, 57th element, it's gotta be a dog. And clearly that may not be the case, but it learns arbitrary features like this, which may not be useful. So to stop this, we drop random information from these networks. So if you do, this is what the visualization of that looks like. You have this very densely connected network, right? And then when we apply dropout, we randomly choose certain nodes to just leave out, which also means that we drop the connections between them. And this reduces this concept called overfitting, which is the process of not learning the features, but learning like just the weird quirks. So then we run this. Once we finish layers.dropout, the last thing that we do is the output function. So here we literally just take one singular node that does the activation. So literally that node right there, and that makes the function. So here, because we're differentiating between two classes, the traditional convention is to use sigmoid. Sigmoid is the activation function that we previously saw here. So that's this one right here. It's very gradual, but it has a nice rate of like accuracy for these problems. And then finally, remember when we imported like TensorFlow.keras.model all the way back? Well, essentially all you have to do is say model is now equal to model, and then the input, which is the image input, and then the output that we're taking is the layers from the dense activation. So you can run this, and then that will compile your model. Is everyone good so far? How are we doing conceptually? That was a lot of information. Cool. Okay. Seems like everyone's doing pretty well. If you guys have any like conceptual questions, feel free to ask. Love answering these. So now, just to sort of visualize our model really quickly, we can hit model.summary, and it'll tell us the total number of parameters that we have. Let's take a look here. How do we know how many nodes to drop out? Good question. So this is sort of a trial and error. So there's a certain number of features inside of our model that we would call hyperparameters. So this is the number of layers, the number of input filters, dropout layers, learning rate. So these are all like tangential things that you can slightly tweak to see if the model performance improves or not. And for our case, we chose 0.5, which means that we dropped half of our nodes. So here we said dropout is equal to 0.5, which is a percentage of the nodes. If we chose to drop out with a higher number, we may start to lose pertinent information. Dropping out is a behavior that you're going to have to trial and error. And this is like a common behavior that you'll reach a lot with machine learning in general, is that you're going to have to learn to sort of be like, why doesn't this work? And then try something else. In fact, the way that we try to learn how machine learning models like figure out stuff is called ablation studies. So we literally like handicap these models by like taking away one crucial component of the network and then seeing what their performance is. And this is like literally how we learn why these models work the way that they do. And we only do dropout in the cases that we expect there's going to be overfitting. If there's going to be underfitting where the model isn't strong enough, we really shouldn't be doing dropout. And I think this is also covered in that like Google Glossary stuff, which is really cool. So if everyone has run model.summary, we can get into the actual process of training. And this is really cool. So this does not take a lot of effort. So we need to initially compile the model first. And all we have to do is import something called an optimizer. So optimizers are essentially, think of it like a reverse Sherpa guide, right? Like a Sherpa guide like helps you sort of find your way up a mountain, right? Optimizers help you automatically change the path and trajectory to find that local, like that global minima of that feature function. So learn the best features and the most optimal set of parameters. For us today, we'll be using RMS prop. You don't have to worry about what this means. If you are interested in this, there's an entire field of study called convex optimization. It is very cool. Just in case anyone was interested. But gradient descent is very, very cool. And there's like some really cool graphs that you can like yield from that. So we're just gonna, you guys should have this, and we say model.compile. And then because we only have 2 categories, we use binary cross entropy. If you have more than one, you're going to use categorical cross entropy. The only thing that changes is the way that it distributes the amount of information for wrong classes. So here, if you say it's a cat, it's like, no, it's a dog. It doesn't have to worry about whether it's a ferret or a seal or like an orca. So the loss or the amount of penalization that the model gets for an incorrect assessment is slightly different. And then the next thing that we have to do is say the optimizer is RMS prop, so the thing that we just imported, and then we set the learning rate. So if you want to sort of get an idea of like, so there's this cool little website if you guys are interested. It's called Neural Network Playground. I'll drop it in chat, but it's sort of like a cute, fun little way of like trying to visualize these models. But essentially what happens is if you just for the sake of examples of what actually happens when you change the learning rate. So at a very slow learning rate, you can see that the output and the feature space very gradually like goes through the process of like of classifying and like learning features. And this is generally pretty good when you have complicated data, right? You don't want it to overfit and then like not actually find the global minima, because sometimes you'll just miss the features, right? Now, what does it look like if you go super fast? It has a completely different learning behavior. So you can see that in a comparable amount of time, it hasn't quite learned the features correctly. And this is because it's missing that local minima. It's looking at this kind of graph and being like, okay, this was not low enough. So then we'll go all the way over here. Well, this wasn't low enough. Then we'll go here. And then it's just going to progressively look this way, but it won't find that optimality point. And it'll learn false features and then just end up in some non-good place. So that's why we set the learning rate as we have to 0.001. And then finally, this is, we want to hold information about the metrics that we've actually done. So you say metrics is equal to ACC. And then this stores our accuracy information. You don't have to worry about this. This is just the data generation process. You can pretty much plug and play with these, with the target size and information. This just modifies all of the images. This stuff for the data generator, when you rescale, what it's doing is normalizing the image. So sometimes we'll have like different images on like different color scales, different whatever, and the channels will be slightly different. So this process normalizes the images so that all of the underlying information is the same for the network. So you can just go ahead and run these 2 slides. It'll say 2,000 images found belonging to 2 classes. The validation one will say 1,000 images belonging to 2 classes. And now we can actually get into the process of training our model. So we say history here because this is actually a dictionary that holds the information about the model, the training and validation accuracy, and the actual model file. And here, what we want to do is from that previous step where we define the train generator with the training data, we provide that. We say the steps per epoch. So an epoch is the number of generations this thing runs. So you saw this thing run for like 800 iterations, right? And that's sort of the learning, the number of times that it looks at a given piece of information. And then we have epochs, which is the total number of cycles in which we go through this information. Essentially, epochs is, okay, we looked at it for a total of like how many generations. The steps per epochs is the number of times that we revisited that specific iteration. Think of it like a nested for loop, if you will. And then here we have validation data. So we just provide the validation generator. And then validation steps is 50. So the reason why these numbers are the way that they are is that we set our batch size. So how many images do we give the model at any given time during training? And it's 20. So because we have 2,000 images, we give it 20, a batch size of 20, and then the steps per iteration is 100. And then here, validation steps is 50 because we have 1,000 images, and then we have a batch size of 20. And remember that it mixes and matches cats and dogs images when it's training this information. So now you can go ahead and just click history is equal to model.fit, and it'll start training your model. Cool. Questions, concerns? Oh. We're just about done, guys. You're at the home stretch. Great job so far. Very cool. Very cool. So how are you guys doing? Is your model training? Cool. Out of curiosity, what is your training speed? So mine is like 18 seconds or 177 milliseconds per step. After we finish, will we be able to upload our own images and see how the model classifies it? Yes. Great question, Meg. So all you would have to do, it's actually a relatively trivial process. So instead, we have this folder here that's like called cats and dogs filter. You just have to replicate this folder structure. So you'd have a train folder with how many ever features that you'd like. You'd have a, oh, that's not good. And then you'd have a validation folder, and then you'd put in your own categories as you'd like. And the same categories. So as long as you're able to replicate the folder structure, you're actually able to try your own data. And see, yes, you are absolutely spot on. Yep, so that's how you would go about doing it. And then let me know when your thing finishes. Mine already finished, but I'm also have a slightly better GPU than you guys, I think. So just a thumbs up when you're done. Oh, yours is done too. Okay, cool. So will someone tell me what kind of overall validation accuracy and trading accuracy that they got? It should be very similar, but I'm curious to see if it's like exactly the same. So your validation accuracy, for those of you wondering, is it's literally called ValAc, and then your training accuracy is called like just ACK. Oh, look at that. So someone got 0.670, someone got 0.749, someone got 0.750. So here we're finding an interesting behavior of machine learning, and which is that it relies on some application of it being random. So based off of the way that the model was trained or which features or nodes it decided to drop out, the accuracy or the validation accuracy that you guys got is slightly different. This is a very difficult problem to contend with. It's interesting seeing what kind of accuracy everyone got. But this is an interesting phenomenon that you'll contend with. So someone will be like, oh yeah, I got like 80% accuracy. And someone else will be like, but I got 78% accuracy, or I got 82% accuracy. And this is very normal. But this behavior is hard to discretely understand. But if we had set random.seed and we had fixed our randomization inside of this function, it would have meant that the training processes would have all been exactly the same. So the nodes that had dropped out, the way that the images were provided to the model, everything would have been fixed. And as a byproduct of this, we would achieve the same validation accuracy. So the last thing that's left, we run visualize intermediate representations. Oh, oops. Again, you're gonna have to change this from catster to just catter, and then dogster to dogster. And then if you run this, it should show you a random image and what your model sees for that random image. So I got this picture of a cat, and then it looks at these features. So here, some of these features, it says like, okay, but like there's nothing here, and it's like black. So this is a feature. This is a phenomenon called sparsity. and it's like a key feature involved with representations of deep learning, and it's essentially like attempting to see which activations are leading to a probable cause of features. So randomly, it chooses to zero out some of the filters just to see what the contributions are. And this should change from time to time. So if I run this again, you'll notice that the result will be slightly different. Slightly different feature representations. And then the last thing, once you're done messing with that, is if you wanted to see your validation and training accuracy, you can see that in the model here. Over the number of epochs and like generations in general, and then the validation and training accuracy that was achieved. Okay. Well, that concludes the workshop and intro to building your own convolutional neural network component. And then for the contest requirements, there's a quick couple of things. The contest is looking at building your own neural network on the basis of what we've done for an image classification task. So the grading criteria is equally split between the creativity of the problem that you're attempting to solve, the sophistication of your network, and then it's equally split, but in my mind, most importantly, the accuracy of your model on both training and validation. This can be for like Pokemon classification. This can be for like literally anything you'd like. And we're curious to see how you guys do. If you guys have any questions for me, any technical questions or resources that you'd like, I'm more than happy to answer any of those. Hope you guys generally enjoyed this workshop that we had. Cool. Where's a good website to find training test data? Kaggle is far and away the best one. So there's this website here. Hello. So there's this website called Kaggle. It's technically owned by Google now, but they're a data science competition website. And they have very, very cool sets of projects. So there are competitions that are going on. They have really, really high data. So there's one about like predictions. Actually, if I go to competitions, so there's like scoring clinical patients. There's like Happy Whale. There's a lot of these ones. You can pretty much choose from a lot of these. Some of these are tabular data. Some of these are image classification data. It's all very cool. And then there's that. Oh, yeah. And then if you guys wouldn't mind filling out some feedback form, Lance just dropped in the chat. It's also in the lectern. That would be awesome. I'm trying to think if there's anything else. Do you guys have any other questions about machine learning in general? Interesting work. There's also like some other ones that's like 6091. I think the deep learning. Oh, is it S191? I think it's S191. How did you go about starting to learn this stuff? Any nice websites that starts from the ground up? Great question. So I learned a lot of my machine learning when I was in high school, and the classes that I ended up using was this course used to be taught by someone called Andrew Ng. He is a very prominent figure in machine learning. But this is like the most foundational course for machine learning. And I think anyone that's like wanting to get into it, this is the best to start. There's actually a version of it on Coursera. So if I go here, Coursera, and then you look up machine learning. So I took this class, excellent resource. And all of the progressions of this class are also immensely useful. So I definitely recommend looking into them. You can take the course for free as an audited thing, but it doesn't include examination. It doesn't include like a certificate if that's something you're interested in. MIT, and then like, I think it's called like, Oh yeah, Deep Race. I always keep forgetting where what the lectures are. Yeah, absolutely. It's a very fun time. What else are you involved in? Um, so currently I work at the I guess this is a more personal question for sure. I work at the Mars lab here at U of A. So I work under Dr. Yun-Sing Ko. So I'm publishing a paper on machine learning this May. And then I work at the Broad Institute, which is a computational biology lab where I work on using machine learning for optimizing gene editing. So there's a lot of like downstream applications, and that's primarily what I work on. Yeah, it's a lot of fun. It's a lot of fun. Yeah, there's a lot of opportunities in like just work environments in machine learning, and like it's a very useful skill to have. It's a very sought after development experience environment wise, and there's a good amount of like legitimate like gap in the industry right now for how many machine learning engineers we actually need. And the compensation is ridiculously good. I think Google DeepMind engineers, like software development engineers, make somewhere in the neighborhood of like 350K USD. How do we get more experience, internship opportunities? This is a really good question. Yeah, Meg, it's crazy, right? So internships, opportunities, and experiences, there's a decent number of courses that I take with machine learning first that I think would be generally pretty useful. So the process of applying for these is very similar to a software development engineering position. You would do interviews and testing. I think, like, obviously, I think all of us studying for exams have gotten Algo Expert. Algo Expert also has like a beautiful ML Expert one. And a lot of the questions that you get asked in interviews are related to this. And they're all very, very cool. So they go through like different conceptual concepts, different like machine learning concepts, and like how to study for them. So when you get asked questions, you can do them. In terms of like internship experiences with machine learning, honestly, your best bet is to do some work at any research labs. Machine learning labs in general are very, very abundant now. Even U of A has quite a few. So if you're interested, I think SAIL is one. So Strong AI Lab, and it's run by Dr. Whitbroke. And then I don't know the names of the others, but I do know there's more than one. SAIL is also like what literally every single, if you try to Google it, it might be a little bit difficult because literally every AI lab calls it that. Where can we get a link for it? Yes, Flex, that is me. Can we get a link for, sorry, Vi, did you want it for the Algo Expert or did you want it for some of the research labs? Oh, yeah, absolutely. Absolutely. I would also just recommend taking ComSci 361. University of Auckland. I think this is the person that you want to contact to get more information if you are curious. Any other quick questions? Yeah, absolutely. Cool. Well, in the case that you guys do have any additional questions, we're probably going to round out this meeting, I'm sure, or unless you guys have like anything else for me. You can always message me or ask me questions and I can try to make the best of them. Absolutely. Thank you, Meg. That was awesome. And yeah, please be sure to fill out the Google form. Tell me what I did. Tell me what was good. Tell me what I could have worked on. Tell me what was interesting. Oh, thanks so much, guys. Thanks for showing up. Glad you guys had fun. Excellent. I love hearing that. It's super interesting. Where can we reach you for specific questions? So my university email is kram416. Yeah, that would probably be the best place to reach me if you had any like specific questions that you'd like to ask. I'll try my best to respond in a time appropriate manner. Leading up to midterms, I might be a little less communicative. If I don't respond to you, just follow up with me. I don't mind pestering. I'll just make a point of responding. Absolutely. Very cool. Oh, there's still some people in here, so. Anything else? Interesting questions, tidbits. And we still have 20 people in here. Would you guys host a follow-up? Sure. What would you possibly, but what would you want the topic to be? Is it just like more or like different kinds of machine learning? Or like a different workshop on like there's a cool. Yeah, there's like a reinforcement learning one that's actually like relatively easy to follow along with. It's called OpenAI Gym, and you learn to balance like a walking stick. So like the stuff that we were doing with OpenAI. So they set up these like simulation environments. So this could be pretty cool. Where like you can play old games of Atari or like it requires a little bit of obviously a little bit of setting up. And I think I can probably set up a collab for this as well, where you can try like Lunar Lander, which is this one's my favorite. So you watch your model generatively learn how to do lunar landings and also learn to land in the right spot. And there are quite a few other ones. This is the one that I was thinking about, balancing a cart pole. They're all very fun. We talked a lot about reinforcement learning. This is some examples of like literally how that happens. Yeah, it's very fun. It's very fun. They also have some excellent tutorials on like their own website. Yeah, I can drop a link for that as well. Keep in mind this is a little. This one does not use the same like plug and play functionality of Keras, so there's a bit of working that's involved with this. Yeah, but it's super cool. Machine learning is like one of the coolest. Like learning about machine learning and artificial intelligence is so interesting. Which papers would you recommend taking in third year for AI ML? So there are 2 papers that are technically available. CompSci 361 is machine learning. It goes over some of the stuff that's similar to what Akash went over, about like super unsupervised learning models, some supervised learning models, and a lot of the theory behind it. 361 is rather substantial. I'm currently the class rep for 361, so I've heard some very interesting feedback about some of the assignments. And there's also 369, which is artificial intelligence. That one is a little less, yeah, Meg, and you took it when it apparently was a little bit harder. So, and then there's also 369, which is literally called artificial intelligence. It's not what you would traditionally consider machine learning, but it's 367. So 361 is machine learning, 367 is artificial intelligence. And 367 is only offered second semester. So if you're interested, I would highly recommend. My friend took that course last semester and he said he legitimately enjoyed the class. Assignments were rigorous, but really interesting apparently. Where is that MIT? It's 119. There's also an interesting thing. Lex Fridman. This guy's a legend. If you guys are ever interested in just doing like a very, like just want to listen to it like a podcasty style thing, Deep Learning Basics and Introduction Overview or MIT 6.S094 is a really, really good place to be. Excellent stuff by this guy. He has a podcast now and he's super cool. Yes, I can. Oh man, he made an updated version in 2021. Oh, that's very cool. Copy link. Unfortunately, I'm not able to answer it. This is only my second semester of being at U of A, so I haven't really had a grasp for like what kind of course offerings there are. Yeah, like AI solving puzzles is super cool. There's like you learn a lot about like learning a lot about chess engines is also very, very interesting. I like very recently started getting like super into chess, so I've been like getting back into chess and like looking into how chess engines solve problems and like reinforcement learning and Monte Carlo simulations is interesting. If you're also like interested in like obviously a lot of stuff that we talked about in this thing was like downstream applications of machine learning. So like how do we understand, like how do we solve certain problems? How do we make self-driving cars work better? Whatever the case may be. The cool stuff, the stuff that I like to work on now is more understanding like the conceptual aspects of machine learning. So it took us years of human evolution to be able to perceive faces, which is like a difficult task, right? Like we had to do this for a lot of time, but now we have the sort of like the privilege and the ability of using machine learning neural networks to see this. So like Google built this thing called hierarchical, it's like beta VAE, Google DeepMind. So Google built this thing that I'm like so unbelievably obsessed with, but it attempts to understand facial features the same way that humans do. And it's just one of those things where you're like, how do you even do stuff like this? So it tries to understand exactly what kind of features we look at as humans, what humans look at. And they found that they were able to replicate human evolutionary behavior with this computational metric, which is so mind-boggling to me. Oh yeah, I really wanted to take 373. It seemed like such an interesting class, although I heard it's very math heavy. Oh, that's good to hear. That's really good to hear. Okay. Any sort of final remarks before we sort of round this out? Again, I think you guys all have my contact information. If not, I'm sure you know someone that does. So, fair game. Thanks so much, everybody. Laters.